Hello everyone. I am Anika Tabassum presenting our work Efficient Contingency Analysis in Power Systems via Network Trigger Nodes with Oak Ridge National Lab and Georgia Tech. This figure, as a motivation about our work, first, this figure is an example of power flow analysis tool where each vertical bars represent different power generators or substations. Contingency analysis in power system means and they analyze the impact of initiating failures or components in the system to find the trigger component. This kind of impact can be measured in terms of several metrics such as voltage loss, line loss, etc. The trigger components in such contingency analysis means the components which, when disrupted, initiate high impact on the system. For example, this figure is actually showing one small demo of a contingency, how contingency analysis can be performed in power systems, where each different bars like A, B, C, these vertical bars are actually showing some kind of transmission substations. And there are also buses involved according to which is connected to each transmission substations and also different generators. So for one contingency analysis, let's say first, if we select A, the measure the impact by disrupting A. That is, components within brown box had some impact due to A. Then again, then select B, measure impact by disrupting B. Select C, measure impact by disrupting C. Now, if we rank all the impact measures among this A, B, and C, the one with the highest impact is the trigger component, that is C. So similarly, for two contingency analysis, we need to select every two components at a time. Example, select A and C, then measure the impact due to their simultaneous failure. Then again, select A and B, measure their impact due to their simultaneous failure. This way, we measure AC like BC this way, and different other combinations of all two components. And then select the set of the trigger components for two contingency analysis will be the set whose simultaneous failure eventually has maximum impact on the system. So analyzing such kind of a contingency analysis for K contingency analysis, and finding K triggers will be expensive as when the order of K becomes high. Since finding this kind of a combination of components and then analyze their highest impact over the system, it will be more brute force or they are combinatorial and hence they become expensive. Now, how can we solve such problem efficiently? So our main idea is to view this problem of finding triggers in a contingency analysis as some kind of a complementary pre-analysis model with using networks. As network-based models, they are inexpensive and hence require less domain knowledge, and they can be applied to for different systems. So we can say leveraging a network for such contingency analysis can capture complex power system dynamics, interactions and interdependencies, and also they can guide experts to adapt to multiple simulation scenarios. For mapping this analysis, we view power system as a network, where if you see this figure, it is actually showing the power system network, where each different colors or each different shapes are actually showing a different types of power components, and the black bars are actually the edges among them, connection that is among the components or among two different heterogeneous components. The four we use for our power system network, the four major power components, and that is power plants, transmission substations, distribution substations, and transmission lines. For limiting the edge connections, we use nearest neighbor approach using geographic distance. For example, let's say power plants, they supply power to the transmission substations. So the idea of connecting the power plants to transmission substations is based on the substations which are near to within a fixed user-defined radius, there will be edges among only those power plants and substations. And in terms of the edges, we also use some logical connections, like based on the components which supply nodes, or the components which actually distributes loads or loads to the other type of components. So next comes our, now we have the power system that has been mapped to a network. So next, how can we identify trigger components from network? Power simulation tools use multiple complex dynamics while analyzing failures. We need a failure cascade model, which can act as a complementary tool to capture such dynamics. So our idea of this complementary network-based model will be a failure cascade model. So for this cascade model, we consider an well-known independent cascade model, a network cascade model, which can be applied on a directed weighted network. So the idea of this cascade is it starts with a given seed of failed nodes as a seed, let's say V1, and then at each step, every failed node has a probability to fail its connected nodes with the probability associated with its corresponding edge weight. So we aim to leverage such kind of an independent cascade model for our failure cascade model. So to capture failure dynamics for contingency analysis, we approach domain-inspired failure cascade model F. Basically, our idea is to develop a model for edge weights inspired from domain knowledge for power failure dynamics. So our idea next is how can we map trigger components in contingency analysis as a critical nodes in the network. As now we are considering everything in terms of a network, and we want to develop a failure cascade model on the network. Now, how can we map trigger components within the network? And we think is considering critical nodes in the network. And by critical nodes, we mean the nodes whose initial failure can cause maximum downstream failures within the network. So if you see this figure, if we select the nodes in the green box, clearly they cause a large failures downstream. That is that all the nodes within the blue box. And we can view them as a critical nodes. And our idea is to map and use this kind of domain-inspired model, failure dynamic model F, which can capture the failure dynamics within this network. And eventually, if we can identify critical nodes using such kind of a failure dynamic model, then eventually they can somehow map to the trigger components in contingency analysis. So next, our failure model F is actually inspired from two concepts of power failures. F depends on two modules. One is propagation probability. When a node fails, the probability that its connected node also fails. For example, if node in the red fails, what is the probability that it will propagate to its child? This is propagation probability. Next one is another one model we consider as a cascade blocking probability, that a node cannot eventually, let's say our node propagate its failure to its child, that is on the black, but this node cannot cascade its failure to its neighbors even if it fails. This cascade blocking model is inspired from a protection system property of power grid. Now, our propagation probability is based on the idea of power load redistribution. That is, if a node has multiple parents, then it may not fail as possibility to have power supply for other parents. See this figure in example figure, where all the circles or the reds are actually power plants, rectangles are in the blue are transmission substations, hexagon or the orange are the transmission lines. And there are three different edges coming from power plant EP2 to all three substations, and each of them is showing a different propagation probability. And the reason is because if you see the TS1, it has actually two power plants as a parent. So even if EP2 fails, it still has a chance of power supply from EP1. Hence, the propagation probability decreased to 1/2. Similarly, for TS2, since it has only one EP2 parent and EP2 fails, so it will eventually definitely fail in TS2 since it has no other chance to get power supply from other power plants. For TS3, in other way, since it has three parents, hence the propagation probability decreased to 1 by 3. So our KIJ model is based on the number of same type of parents that the child eventually has. Next comes our cascade blocking probability, that the model depends on two different models and two different, which is inspired from two different domain knowledge. First is the transverse model. This type of model is only applicable for the edge where is the only transmission line is present. So the domain knowledge is the high voltage transmission line have more chance to cascade. This figure shows an edge connected to a transmission line and distribution substation. And we can choose high voltage transmission line as small difference of Vi minus V. And by V is actually the acceptable voltage limit. So next, another domain knowledge comes in terms of a sibling distribution model, which is applicable for the edges with transmission line in connected nodes. And the domain knowledge is based on the protection property model in power systems. Overall idea is if a parent fails, it stresses the protection system of the child. This stress eventually increases if the child has many neighbors. And for our model, we view different neighbors of nodes as siblings. And this figure actually, for example, this figure actually shows three different transmission substations and each has a common parent EP1. That means they are all these, since they are common parents, all these three are actually siblings. And we view this protection model as uniform distribution based on the number of siblings a node has. So now to finalize our failure cascade model F, our power component failure is important for contingency analysis if it has the first one, if it has the ability to fail its neighbor, which can also cascade. And also F is also based on the probability that both based on the both properties like propagation probability and cascade blocking needs to occur together. And propagation probability is the probability that a node edge can fail by propagation, and cascade blocking is the probability that the node can eventually cannot cascade. So for our propagation probability or failure model is depends on the node can propagate its failure to the child, and eventually the child also can cascade. This is the summary of our domain-inspired method in heterogeneous network, DIHAN. And our idea is to use IC independent cascade model as a failure cascade, where the edge weights are from the are based on the domain-inspired failure model F. And we need to identify the set of K critical nodes that can cause maximum downstream damage on G using IC. This problem can be mapped as an influence maximization, which we can solve using a fast greedy heuristic. So for experiment data sets, we construct a national level power system network in collaboration with Oak Ridge National Lab using publicly available geographic shapeless file data. The domain-centric national network is supplied by power experts, where edge connections are defined by the experts in contrast to the geographic distance. And the regional networks are considered for analyzing based on the major grid connections in US. So now how can we evaluate the set of critical nodes S? Our main intuition is to check whether network-based critical nodes match with the trigger nodes in the power simulation, which was our main motivation for developing failure model F for DIHAN model. So to measure this kind of that the nodes eventually the set of critical nodes can be trigger components, we get some criticality criteria of components based on the attributes that what generally power experts usually check in their contingency analysis. The table shows some of these criticality criteria of trigger components recommended by power expert. So one such criticality criteria, let's say criteria R1 is actually like high voltage transmission lines. That is, they need to be greater than equal to 345 kV. So similarly, one such is the load needs to be greater than 300 megawatt, for power component. And also the experts also check whether a particular power component is near a very user-defined critical nodes like a military base facility or something. So next, to compare based on such criticality criteria, we also propose up the performance, and to eventually evaluate the performance of our set of critical nodes with respect to the expert provided criteria. We propose a metric called M gain. The M gain is basically the ratio or coverage gain, where the numerator shows that among k nodes in S, how many of them satisfy a criteria, and Rx it basically represents a given criteria, and where Z is the indicator function showing if the given node Si follows the corresponding criteria. Denominator shows among all M nodes in the network how many nodes actually satisfy Rx. Basically, this is the ground truth, or originally what fraction of nodes are actually present that can satisfy Rx. So for baselines, we select non-domain inspired edge weights, and our intention is to check how careful edge weight leverage against non-domain inspired model. These three figures are the baselines using uniform edge weights, and the base by uniform edge weight I mean the keeping all the edge weights as the same value, but use the same Diamond framework for selecting the critical nodes. Let's say for edge weights, we use different values. For example, IC1 means selecting k nodes using Diamond method, keeping edge weights equal to 1. So each of these three figures is actually showing our performance for different models, for different criticality criteria. And each vertical bars is actually showing a different model, where red bar is actually our model Diane, and x-axis shows different data sets we used, and y-axis shows the M gain metric. Each figure represents the performance with respect to a different expert given criteria. And our model consistently outperforms all the baselines and show that non-domain inspired models of uniform edge weights, they cannot eventually find critical nodes that can be useful for contingency analysis. So we also compare with the popular network centrality measures, where like one and such popular network centrality like page rank, PR is the page rank, based on the entire network we used, and the CS is actually an aggregated centrality measure based on page rank and reverse page rank. And CS, let's say CS01 shows the aggregated, what is the aggregated weight we used for page rank and the reverse page rank. Let's say 0.5, 0.5 means for the page rank, we take half of the weight of the page rank and half of the weight of the reverse page rank. And for these models, we select top k nodes with high centrality, and our model consistently outperforms, show and that network dynamics is also more important than network structure. So we also did ablation experiment where we want to show every variant to model failure. Our failure model F is important. So for that, we select edge weights using different each variant of F separately and select our critical nodes using the same method as Daihan. So for example, that Daihan is actually our original model where we used both propagation probability and cascade blocking, where CB is actually the model we used edge weights only based on cascade blocking, FP based on only on the propagation probability. No expert rule, or NER is where we remove the transvolt model from the edge weight, and then random Gaussian is based on the Gaussian distribution, where keeping the mean and the variance as the same as our Daihan model F. So here in this model, each black vertical bars actually show error bars or model deviation after we run 1000 different cascade simulations. And so similarly, each different figure is also for each different expert provided criteria. And we also, and red is our original model, Diane. So we consistently outperform all other variant of F, which is showing considering all variants of F for edge weights are actually important. So we also analyze that the selected nodes using Diane can be used for real contingency analysis simulations by leveraging high fidelity simulation analysis on the power system of ERCOT. And that has been conducted through by the power experts through our in-depth analysis, in-depth study on the contingency analysis on this ERCOT power system. For the analysis, the experts first conduct a base case analysis, that is ideal scenario when no components are removed. Next, they create multiple simulation scenarios, each time removing a different subset of transmission lines. And they record different parameters compared with the base case scenario, and the amount of load loss, number of nature of components which cause voltage violations, the simulation is convergent or not, this kind of parameters. Based on these above comparisons, next the experts rank each transmission line. And we check that whether the attributes of the components that experts rank are and they are high in the contingency analysis also match with the node selected by our model Diane. And so this figure is actually showing all the attributes we consider that expert and also our MGAIN or Diane model based on this kind of an attributes for the same type of network. And so in all the attributes from R6 to R8, Diane gain on average is 25.3, and for R8, which is a potential attribute for a simulation to not converge, the coverage gain of our Diane is almost more 21x. To summarize the entire work, we consider a power system as a heterogeneous network. We build a domain-inspired model, Diane, for setting up probabilistic edge weights. We show network dynamics is more important to select critical nodes than network structure. We show our network-based critical nodes can act as complementary solution for triggers in contingency analysis to expedite high-fidelity simulation tasks. And last, we initiate the idea of how to incorporate domain knowledge in power system domain. Thank you all. You can find our paper, datasets, and all the codes as available in the given link. Thank you.